page 6 and the final page of the second semester exam review for geometry. In this first set of directions, it says solve for x. Assume the lines that appear to be tangent are tangent. Okay, so the theorems at play here, and first ones, and maybe both of them are easier to draw. So the first one we'll look at is when two segments or two chords, we could even say, intersect. So two chords intersect, and they look like they intersect they look like they bisect each other, but they don't have to be. That doesn't have to be the case. It could look more like this. So those chords intersect, and each chord is split into two parts. So I'm going to call this A and B. That one chord, in fact, I'll change it to red. The red chord is split in section A and section B, and then the blue chord that I'm going to highlight here, we could call that C and D. And what we know about this is that A times B is equal to C times D. So that's one theorem that we learned there. Actually relates back to similar triangles. The other one is when you have a circle, and oftentimes it's two secants intersect outside the circle. And this one was a little bit different. And what we said here was the outside part, so outside segment times the entire segment. So the entire segment is equal to, and we can do kind of the same thing on the other side. I'm going to go off our page a little bit here, but is equal to the outside segment I'm actually going to change up here, times the entire segment. And over here, I'm actually going to change this too. Let's change the entire segment to blue. So outside segment times entire segment. Okay. This actually holds true for if you have a secant segment as well. I mean, a tangent segment. Maybe you have one like this, and then an entire segment like this. For the green one, the outside part is the whole segment. So you can say green segment times green segment. So here we go. We'll look at these in a couple examples. So number 47 fits our first one on the top right here. So all we have to do here is we can say 5 times 5 times 8 is equal to 4 times x. And we just solve. So we have 40 equals 4x, so x equals 10. 48 here, this is the ones you have to kind of be careful with. We have an outside part, so 32, times the whole or the entire segment. Well, the entire segment is 32 plus x. This is where a lot of people make a mistake. They just do 32 and then they just do x, but it's the outside part times the entire segment equals, and this isn't tricky, but it's a little odd how we say it, but the outside part of this one is 40. It doesn't go inside the circle at all. However, the entire segment is also 40. So you actually can write 40 squared. So we need to solve this. We're going to distribute. So we get 32 times 32, which is 1024. plus 32x equals 40 times 40 is 1,600. Subtract 1,024 from both sides. And so we're going to subtract that. This is going to be 32x. If we subtract over here, we get 576. And then 576, we're going to divide both sides by 32. So 576 divided by 32 equals 18. X equals 18. And then the final one from this section, similar to the last, we have outside part. So 7 times the entire segment. I'm going to section this off here. The entire segment is 7 plus 17, so 24, is equal to the outside segment, 8 times the entire segment, x plus 8. And we're just going to solve 7 times 24. So this is 168 equals, we'll distribute here, 8x plus 64. Subtract 64 from both sides. And you get 104 equals 8x, dividing 104, or dividing both sides by 8, we get 13. So x equals 13. All right, moving on to trigonometry. State the following definition. Sine of an angle. Well, that we can remember SOHCAHTOA, and that is opposite leg over the hypotenuse. Cosine, or CA, I'll just write it down here, is adjacent leg over the hypotenuse. And tangent is opposite leg over adjacent leg. So those are the definitions, and then we can use those to solve triangles. This one just says find the missing side. So we don't have to solve the entire triangle, so let's look through this. This is 39. It's the angle we're working with. X is opposite that, and 10 is the hypotenuse. So we're thinking to ourselves, which trig ratio deals with opposite and hypotenuse? Well, that is sine. So we write the sine of 39 equals opposite, which is x, over hypotenuse, which is 10. I actually, before I put it in my calculator, I would just write that I'm going to multiply both sides by 10. And I'm going to plug that in our calculator, 10 times the sine of 39. And we get 6.3. It says round to the nearest tenth, so 6.3. We could keep going and solve more, but it doesn't ask us to, so we'll just stop there. Next one. Find the measure of the indicated angle to the nearest degree. This time we want to find this angle. I'm going to call it A because I don't like using question marks. So with respect to angle A, we have the 15 and the 29. Well, those are both legs. This is the opposite, and this is the adjacent. So which trig ratio deals with the opposite leg and adjacent leg? That is tangent. So we write tangent of the angle, which we don't know. We're calling it A, equals opposite over adjacent. You can do 28 over 15 in your calculator. You don't actually need to. So you can do inverse tangent of both sides over here, inverse tangent and tangent cancel, so we have A equals, and I'm going to do inverse tangent of 28 over 5, so make sure you do second tangent, 28 divided by, sorry, not 5, divided by 15. So angle A is 61, actually it says nearest degree, so it's not 61.8, we're going to go to the nearest degree of 62 degrees. And last one here is an application that we get to use trigonometry. We're finding the area of this regular pentagon. And so area of a regular pentagon is 1/2 perimeter times apothem. So we start filling things in. Perimeter, it's pretty easy to find. This side is 3. There are 5 of those, so perimeter is 3 times 5, which is 15. So perimeter is 15. And then we need the apothem, and that's where the difficulty comes in, but not too bad. So trying to find the center here. So we need the apothem. And so what we do is we section off this little triangle. Sorry about that line. And we know that this entire circle is 360 degrees. If we had this triangle here, like the dotted orange to the solid orange, that would be the 360 divided by 5. But there's 5 of those equal triangles. 360 divided by 5, 72. Oops. So that's 72, but we don't want that whole thing. We just want this part. Let's put it in black. So 72 divided by 2 is 36. In fact, we learned it's even better to find this one. So 90 minus 36 is 54. And this is our apothem. So we see we can use some trig. I'm going to come all the way over here. The apothem is the opposite leg, and then this squiggly black is the adjacent leg, and that's 1.5. So what works with opposite and adjacent? That's tangent. So the tangent of 54 is opposite, which is A, over adjacent, which is 1.5. I would just go ahead and multiply both sides by 1.5 here. And put that in my calculator. So the apothem is 1.5 times the tangent of 54. The apothem is 2.065. 2.065. I know I'm going more than the 10th, but I like to be accurate, a little more precise here. So my answer doesn't get off at all, which I don't think it would. So the area we just now have to multiply. So we have 0.5 times 15 times 2.065. 15.4875, but it says round our answer to the nearest 10th. So this is 15.5, and this is inches squared. So kind of a multi-step question there. And that is the end of the exam review.